NEC Article 700 defines the requirements for electrical systems, including emergency power systems. While not directly applicable to every situation, it provides guidance on the use of mineral-insulated cables in emergency power systems. NEC Article 695.8 A4 requires the use of mineral-insulated cables for fire pump circuits due to their resistance to fire and ability to maintain circuit integrity in high-temperature conditions. This ensures that the fire pump is able to operate even in the event of a fire. In the absence of specific requirements for mineral-insulated cables in emergency power systems for non-fire pump applications, you should refer to NEC Article 701, which applies to emergency power systems. NEC Article 701.5 B2 requires that feeder cables for emergency power systems be installed in raceways with at least a 2I fire rating. This includes cables from the generator to the distribution panels. Technically, the feed from the generator is not considered a service entrance, as it is not the primary source of power. However, it is similar to a service in that it provides backup electrical power. While mineral-insulated cables are not explicitly required, they offer significant advantages in terms of fire resistance and circuit integrity. For this reason, it is generally recommended to use mineral-insulated cables for feeder circuits in emergency power systems, regardless of the type of load being served. When designing an emergency power system, there are several important factors to consider. These include, firstly, compliance with the National Electrical Code. Secondly, local codes and regulations. Thirdly, the specific equipment and loads being served by the system. Fourthly, ensuring adequate capacity and reliability. Fifthly, designing the system with redundancy and proper control to prevent overload. And sixthly, ensuring an uninterrupted power supply during an emergency. The NEC provides specific guidelines for emergency power systems. Article 700 covers emergency systems, Article 701 addresses legally required standby systems, and Article 702 discusses optional standby systems. It is important to understand which articles apply to your specific situation. Local codes and regulations may have additional requirements or restrictions beyond those outlined in the NEC. Always consult with local authorities to ensure compliance. Carefully consider the specific equipment and loads that the emergency power system will be serving. This includes lighting, fire alarm systems, computers, boiler room equipment, and pumps. Determine the power requirements of each load and ensure that the generator has adequate capacity to meet those needs. Reliability is critical for emergency power systems. Choose high-quality components and follow best practices for installation and maintenance. Regularly test the system to ensure that it is functioning properly. Redundancy can improve the reliability of an emergency power system. Consider using multiple generators or automatic transfer switches to provide backup in case of a failure. Proper control is essential to prevent overload and ensure an uninterrupted power supply. Use automatic transfer switches to switch between the normal power source and the generator. Implement load shedding to prioritize critical loads during an emergency. Mineral-insulated cable, often referred to as mineral-insulated metal sheath cable, is a specialized type of electrical cable known for its exceptional fire resistance and durability. Its construction consists of copper conductors encased in a tightly packed mineral insulation, typically magnesium oxide, all within a seamless copper or stainless steel sheath. This design provides superior protection against fire, moisture, and mechanical damage, making it suitable for critical applications where circuit integrity must be maintained even under extreme conditions. Firstly, mineral-insulated cable exhibits excellent fire resistance, capable of withstanding temperatures up to 1000 degrees Celsius or 1832 degrees Fahrenheit. The mineral insulation does not support combustion, preventing the cable from contributing to the spread of fire. Secondly, the cable's construction ensures high resistance to moisture and corrosion. The seamless metallic sheath protects the conductors and insulation from water ingress and chemical exposure, making it suitable for use in damp or corrosive environments. Thirdly, mineral-insulated cable is highly resistant to mechanical damage. The robust metallic sheath provides excellent protection against impact, crushing, and abrasion, ensuring long-term reliability in demanding applications. Fourthly, the cable's design allows for high operating temperatures, typically up to 250 degrees Celsius or 482 degrees Fahrenheit. This makes it suitable for use in high-temperature environments where conventional cables may degrade or fail. Fifthly, mineral-insulated cable offers excellent electrical conductivity due to the use of copper conductors and the tightly packed insulation. This ensures efficient power transmission and minimizes voltage drop. Common applications of mineral-insulated cable include, firstly, fire alarm systems, where circuit integrity is critical for alerting occupants in the event of a fire. Secondly, fire pump circuits, where the cable must maintain power to the fire pump to ensure its operation during a fire. Thirdly, emergency lighting systems, where the cable must provide reliable power to emergency lights to guide occupants to safety during a power outage. Fourthly, critical control circuits, where the cable must maintain signal integrity to ensure the proper operation of essential equipment. Fifthly, high-temperature environments such as industrial ovens, furnaces, and heating equipment, where conventional cables may not be suitable. Mineral-insulated cable is installed using specialized fittings and termination techniques. The cable is typically terminated using compression fittings that provide a secure and watertight seal. Special tools are required to strip the cable and prepare it for termination. The NEC provides specific requirements for the installation of mineral-insulated cable in Article 332. These requirements cover topics such as support, protection, and termination. The NEC defines emergency systems as those systems legally required and classed as essential for safety to human life. Emergency systems are intended to automatically supply illumination, power, or both to required locations in the event of failure of the normal supply. Legally required standby systems are those systems required and so classed as essential for safety to human life. Legally required standby systems are intended to automatically supply illumination, power, for both to required locations in the event of failure of the normal supply. Optional standby systems are those systems that supply illumination or power to aid in the restoration of normal operations. Optional standby systems are typically installed to protect private business or property where life safety does not depend on the performance of the system. The NEC provides specific requirements for emergency systems in Article 700. These requirements cover topics such as wiring methods, power sources, transfer switches, and overcurrent protection. The NEC requires that emergency systems be designed and installed to provide a reliable source of power in the event of a power outage. The system must be capable of automatically transferring to the emergency power source within a specified time frame. The NEC requires that emergency systems be tested regularly to ensure that they are functioning properly. Testing must be performed in accordance with the manufacturer's instructions and the requirements of the authority having jurisdiction. Article 700.12 describes permitted power sources, for example 700.12. A covers storage batteries, 700.12. B covers generator sets, 700.12. C covers uninterruptible power supplies, and 700.12. D covers separate services. Article 700.10 outlines general wiring requirements, with 700.10. A covering wiring independent of other wiring, and 700.10. B covering wiring common to other wiring. Article 700.12. The 6 outlines that internal combustion engines used as prime movers shall be suitable for use with one of the fuels specified as follows: firstly, natural gas; secondly, liquefied petroleum gas; or thirdly, diesel fuel. The generator set shall have as signals for firstly, derangement; secondly, overspeed; thirdly, high engine temperature; fourthly, low oil pressure; fifthly, battery charger malfunction; and sixthly, overcrank. Emergency lighting is a critical component of any emergency power system. Emergency lighting provides illumination to guide occupants to safety in the event of a power outage. Emergency lighting must be designed and installed to provide adequate illumination to all required areas. The NEC requires that emergency lighting be tested regularly to ensure that it is functioning properly. Fire alarm systems are another critical component of emergency power systems. Fire alarm systems detect fires and alert occupants to evacuate the building. Fire alarm systems must be designed and installed to provide reliable detection and notification. The NEC requires that fire alarm systems be tested regularly to ensure that they are functioning properly. When designing an emergency power system, it is important to consider the specific needs of the building and its occupants. The system must be designed to provide adequate power to all critical loads and to ensure the safety of occupants in the event of a power outage. The system must be installed and maintained in accordance with all applicable codes and regulations. A transfer switch is a device that automatically transfers the electrical load from the normal power source to an alternate power source when the normal power source fails. Transfer switches are an essential component of emergency power systems. They ensure that critical loads continue to receive power during a power outage. There are two main types of transfer switches. Firstly, automatic transfer switches, and secondly, manual transfer switches. An automatic transfer switch automatically transfers the load from the normal power source to the alternate power source when the normal power source fails. An automatic transfer switch typically uses a voltage sensing circuit to detect a loss of power on the normal power source. When a loss of power is detected, the automatic transfer switch automatically switches the load to the alternate power source. A manual transfer switch requires a person to manually transfer the load from the normal power source to the alternate power source. A manual transfer switch is typically used in smaller emergency power systems where automatic transfer is not required. Transfer switches are rated by the amount of current that they can carry. It is important to select a transfer switch that is properly rated for the load that it will be serving. Transfer switches must be installed in accordance with all applicable codes and regulations. Overcurrent protection devices, such as fuses and circuit breakers, are used to protect electrical circuits from overloads and short circuits. Overcurrent protection is an essential component of any electrical system. It prevents damage to equipment and reduces the risk of fire. Fuses are overcurrent protection devices that contain a fusible link that melts and opens the circuit when an overcurrent occurs. Circuit breakers are overcurrent protection devices that use a mechanical mechanism to open the circuit when an overcurrent occurs. Circuit breakers can be reset after they trip, while fuses must be replaced. Overcurrent protection devices are rated by the amount of current that they can carry. It is important to select overcurrent protection devices that are properly rated for the circuits that they will be protecting. Overcurrent protection devices must be installed in accordance with all applicable codes and regulations. Grounding is the process of connecting electrical equipment and systems to the earth. Grounding provides a path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock. Grounding is an essential component of any electrical system. It is required by the NEC. There are two main types of grounding. Firstly, equipment grounding, and secondly, system grounding. Equipment grounding is the process of connecting the non-current carrying metal parts of electrical equipment to the earth. This includes the metal enclosures of electrical panels, motors, and other equipment. System grounding is the process of connecting the neutral conductor of an electrical system to the earth. This helps to stabilize the voltage of the system and provides a path for fault current to flow back to the source. Grounding electrodes are used to connect electrical systems to the earth. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. Grounding conductors are used to connect electrical equipment and systems to the grounding electrode. Grounding conductors must be sized in accordance with the NEC. Grounding must be installed in accordance with all applicable codes and regulations. Bonding is the process of connecting different metal parts of an electrical system together. Bonding helps to create a low impedance path for fault current to flow back to the source. Bonding is an essential component of any electrical system. It is required by the NEC. Bonding jumpers are used to connect different metal parts of an electrical system together. Bonding jumpers must be sized in accordance with the NEC. Bonding must be installed in accordance with all applicable codes and regulations. Surge protection devices are used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, switching operations, and other events. Surge protection devices divert the surge current to ground, which helps to protect equipment from damage. Surge protection devices are rated by the amount of surge current that they can handle. It is important to select surge protection devices that are properly rated for the equipment that they will be protecting. Surge protection devices must be installed in accordance with all applicable codes and regulations. Maintenance is essential for ensuring the reliable operation of an emergency power system. Regular maintenance can help to prevent failures and extend the life of the system. Maintenance tasks for emergency power systems include, firstly, inspecting the generator for any signs of damage or wear. Secondly, checking the oil level and coolant level in the generator. Thirdly, testing the generator under load to ensure that it is functioning properly. Fourthly, inspecting the transfer switch for any signs of damage or wear. Fifthly, testing the transfer switch to ensure that it is functioning properly. Sixthly, inspecting the batteries for any signs of damage or wear. Seventhly, testing the batteries to ensure that they are properly charged. And eighthly, keeping the area around the generator and transfer switch clean and free of obstructions. Records of all maintenance activities should be kept. Emergency power systems should be inspected and tested regularly by a qualified electrician. NEC 701.15 covers the testing and maintenance requirements for legally required standby systems. The informational note number 1 under 701.15. A talks about where to find more information from manufacturer's instructions, NFPA 110 and NFPA 70B. The maintenance and testing programs shall include all the manufacturer's routine maintenance requirements and shall be conducted according to the manufacturer's instructions. Instructions shall be available for examination by the authority having jurisdiction. A written record shall be kept on such maintenance and testing. The generator set, including the prime mover, shall be exercised with load at least monthly. The monthly test shall be conducted for a minimum of 30 minutes.